And here we go. Okay, so the first thing we're going to do today is go over the quiz problem. This should take about 10 minutes, and then we'll launch back into the lecture, okay? And we'll actually finish up today our lecture on electric fields. So next week, we're going to move on to a new topic. Okay, so on the document cam, here's the quiz. The first thing we should do is remember that each one of these is a point charge, and we know that the electric field due to each one of these is given by Coulomb's law. But of course, we also have to remember that electric fields are vectors, so we're essentially adding two different vectors together. It's helpful to actually just put each vector on the page. So how about we start with this? Charge number 1. It has a negative sign, doesn't it? Yeah. So what direction is the electric field going to be when considering a negative charge? Towards the negative charge. So I'm going to draw a line that connects my field point P to the charge, and then I'm just going to show the electric field vector, which we should label as E1, pointing directly towards it, right? What about for the second charge? It's a positive charge, so the electric field points away from it. That means if we're considering this point right above the charge, this electric field is pointing straight up. And that one will be labeled E2. Okay? So we've got E1 and we've got E2. E2, that one is simpler to deal with, right? Because it only has a Y component. E1, on the other hand, has an X and a Y component, so let's label those components on the diagram. So this will be E1X, and this will be E1Y. There is an angle here inside of the right triangle we've just constructed, which I'll call theta. We're going to refer to that later on. But let's also notice the same angle theta appears here in this larger triangle that has the same proportions. Okay? All right, so let's write down some equations then. The total electric field, which I'll call E total, is equal to E1 plus E2, which are both vectors. And what we're going to do next is write each one of these vectors in XY component form. So for E1, how would I do that? Let's write E1 in XY component form. So I will take, for the X component, the magnitude of E1 times what? Cosine of theta. That will pick out the X component of this vector. And then that is accompanied by the I hat unit vector to denote the X component. What about for the Y component? Okay, so it would be magnitude E1 times sine of theta. But also it has a negative sign because it's going down towards the negative Y direction. And this is accompanied by the J hat unit vector. All right? What about E2? This is easier to deal with, right? What is the X component for E2? 0. Just 0. So I'll write that as 0 I hat and then plus what? E2. Just the whole magnitude of E2 is the Y component. That's always the case when you have a vector that points along one direction alone. That component will be just the magnitude. Okay, so it looks like when we add these together, I'm going to have for the overall X component, just this, E1 cos theta. And for the overall Y component, I'm going to have to add these two together, which is magnitude E2 minus magnitude E1 sine theta. So just to be clear, this is my overall X component. I'll write that as E total X, and this is my overall Y component, which I'll write as E total Y. So does that make sense so far, what we're doing? Okay, so whenever we have to write the magnitude of one of these electric fields, here's how we're going to do that. We're going to use Coulomb's law. So whenever a magnitude of an electric field appears, this is what we're using. We're using K times Q divided by R squared. And just remember, we are dealing with a negative charge in Q1. But when we apply this equation, which is referencing just the magnitude We don't need to put the sign in there. We've already accounted for that in our picture, okay? So for each one of these, we have an R. Q is pretty straightforward. We just have those values. But what about R? For the first charge, what is my R value? It's this basically hypotenuse that we've constructed, right? So this would be my R1. How would I calculate it? Square root of 30 squared plus 52 squared. And these aren't centimeters. And what does that work out to, everybody? What do we get? It's like 60 on the dot, right? So 60.0, keeping our 3 sig figs, okay? Okay, what about our sines and cosines? Let's work those out just on the side. Because we have a sine here, we have a cosine here. Better figure out what those are. Actually, before we do that, what's R2? 30. Because the distance between the second charge and the point is just this 30 centimeters. So that's R2 right there. Okay, so now let's deal with the sines and cosines. Sine of theta, let's do that first. So using this big triangle down here that we see, how would I express the sine of the angle theta? Yeah, so sine is opposite over hypotenuse, so that's 30 centimeters over here is the opposite side divided by 60 as the hypotenuse. So just about a half, isn't it? Okay, what about cosine? That would be the adjacent side over here, which is 52 divided by 60, right? Okay, so we've set the whole thing up now. The rest is kind of just plug and chug. So let's do E total X. Just in the interest of saving time, I'm going to leave off the units when I write everything down. But just remember, I'm going to convert all the centimeter units to meters. I'm going to have to do that to get the units to work out, okay? So for E total X, we have magnitude of E1, which is K times Q1 divided by R1 squared. So K is 8.99, 10 to the 9. Q, and we're using the magnitude of the first charge here, which is 86 microcoulombs, or 86 times 10 to the minus 6 in coulombs, divided by R1, which we said is 60 centimeters, but that would be the same as 0.6 meters, and we're squaring that distance. So that's the magnitude of E1. Make sense? That gets multiplied by cosine, which is 52 divided by 60. And that's our overall X component. So can someone crunch those numbers for me? You might have done it on your quiz. What do we have? 1.86, 10 to the 6 newtons per coulomb. Do we agree? So try it out to see that's what you get, but that's what you should be obtaining. For E total Y, we have to do this whole calculation. So it's the magnitude of E2 minus the magnitude E1 sine theta. For the magnitude of E2, we're using Coulomb's law, which is 8.99, 10 to the 9. The charge is 50 microcoulombs, so we want to put that in coulombs. Micro is 10 to the minus 6, remember? This is 50 times 10 to the minus 6 coulombs. Then our distance is just 0.3. And we're squaring that distance. Okay, that's our R value. Okay, then we subtract magnitude E1, which is actually just this whole thing we wrote down earlier, right? But this time picking up a factor of sine theta. So just to repeat, we have 8.99, 10 to the 9. And then we have 86, 10 to the minus 6. And then we divide by 0.6 squared. But again, we're multiplying by sine theta, which is 30 over 60. Now this works out to something positive. What do we get for this one? tell you. We get 3.92, 10 to the 6 newtons per coulomb. All right, so we're almost done. We found the total electric field, but we did it in x, y component form. So what we want to do next is just take those x and y components and convert them into a magnitude and a direction. Okay, so how did we do that? How can we take what we found here and get the magnitude? It's the Pythagorean theorem, yeah? So for the magnitude of E total, just like with any other vector, if you want to take the magnitude, take the square root of the x component squared plus the y component squared. So in other words, I'm going to take this y component and this x component and plug them into this formula, okay? And what does that give us when we do that?
6.35 times 10 to the 6 times per coulomb.
You might want to check again on that one.
4.34.
4.34. 10 to the 6 newtons per coulomb. So that's the strength or the magnitude of the electric field at that point. What about the angle? How do we deal with this part? Yeah, this is the arctangent. So remember, tangent of the angle of your vector is the y component divided by the x component. So to get the angle itself, we would just take the inverse tangent, or you could say arctangent, whatever. It's the same thing. And what do we get when we plug these numbers in?
65 degrees.
Yeah, so it's like 64.6 degrees. So overall, this is the strength of the E field, and it's pointing in this direction. So pretty straightforward, hopefully. I know these calculations aren't necessarily easy because there's a lot of places where you can mess up a sign or something, but hopefully the big picture is pretty straightforward as to what we're doing here. Okay? So any questions? Yeah.
So the 64.6 degrees is actually from the negative y-axis, right?
No, so here, let's be clear. That angle, let's draw the picture. This is our E total vector, right? And it has an x component, which is positive, and a y component, which is also positive. So we know it's kind of in the first quadrant like this. The angle I'm talking about is this one right here. Because think about how we just set up the tangent equation. Tangent of this angle should be opposite over adjacent, right? The opposite side is y, the adjacent side is x. That's how we got this. Anything else? Okay. So there's your first quiz. You survived it. That's good. Let's go back to the lecture. Here we go. All right, so everybody, settle down. We're almost done with this lecture on electric fields. So we have maybe like 8 slides to get through. And then hopefully we can spend a little time at the end just going over some practice problems. That will be useful. So let's just jump right back into it. The last thing we were talking about is the motion of an electric charge when it's inside of an electric field. Okay? And we saw some examples of that using our kinematic equations. What I'm going to show you now is another example of how a charge moves when it's in an electric field, but this motion is slightly more complicated and we're going to analyze it in a lot of detail. So here's what's going on. We have a charge Q. Let's assume that charge is positive. And it's uniformly distributed on a ring, which lies in the xy plane that you see here. The radius of this ring is r. Okay, we already worked out what the total electric field due to this ring of charges. We did this last week when we were doing these integrals. And remember, we found that the x component, as long as we're talking about a point on the z-axis, is equal to 0, and so is the y component. So if we're at some point on the z-axis, there's only a z component for the electric field. So it's either just like pointing straight up like this or straight down like that. And we worked out a formula for that z component, which is given here. Okay? So I know that's probably not looking like the most familiar thing in the world, but remember, we did work this out last week. Okay, so that's the formula for the electric field in this situation. So now, let's suppose that we put an electron on the z-axis right here. And we're not going to put it very far away from the ring. We're going to put it relatively close to the ring. So what do I mean by that? Z is going to tell us where the electron is located. So if z equals 0, it's right here at the center of the ring. If z is positive, it's up here. And if z is negative, it's down here somewhere. We're going to say that z is very, very small compared to r. So it's staying very close to the ring. My claim here is, in this situation, this electron is going to undergo simple harmonic motion. You remember this from Physics 45? Simple harmonic motion? That's another way of saying the electron oscillates up and down. Let's just try to get a general sense of why that is. The ring has a positive charge, doesn't it? And the electron has a negative charge. So it's going to be attracted. If we put it up here, the ring is generally speaking pulling it down, right? But it will move down and then overshoot the center, right? It's not just going to stop at the center. It's going to keep going. But once it's down here, it's still being attracted to the positive charge. So now it's feeling a force up, which is slowing it down. Eventually comes to a stop. It's still being pulled up, so then it turns around, moves up again, and then that process repeats. So you can kind of see how you get this oscillating type motion. So what we're going to do is work out in detail how we get that sort of oscillating motion out of this situation. Okay? So are we all cool with the setup here? Any questions so far? Okay, so the first thing I'm going to do is take that expression for the electric field, which again is something we derived last week by integration. And I'm going to make an approximation. Remember, we have this idea that we have some formula and we can approximate it by only keeping the first order terms in a Taylor series. So we're going to do that kind of thing to the formula for EZ that we found. And for that, we're just going to do it on pen and paper. So we'll start with the formula. The electric field in the z direction, due to this ring of charge, is equal to Q divided by 4 pi epsilon naught. And then we have z divided by z squared plus r squared raised to the power 3/2. So that's the formula we're starting with. Okay? So what I want to do with that formula is kind of rewrite it in a slightly different way. Same constants are up front. We have q divided by 4 pi epsilon naught. And then I'll keep the z on the top, but instead on the bottom what I'll do, we have this thing z squared plus r squared going on, right? What I'm going to do is pull out an overall factor of r squared from z squared plus r squared, okay? So if I pull out an overall factor of r squared, then we'll have z squared divided by r squared for the first term. And if you put the r into the parentheses, just gives you back z squared. And then since we pulled out the r squared for the second term, I'm just going to have plus 1. So you all see that? Okay, but that whole thing is being taken to some power, which is 3/2, correct? Okay? All right, so let's try to simplify this. If I have r squared here, and I take that to the 3/2 power, what does that equal? So what is r squared 3/2 power? That's just r cubed. You can just multiply these powers together. So this is better written as just a simple r cubed. So I'm going to pull that r cubed factor out to the front and just put it with these other constants. Okay? So therefore we have EZ equals q divided by 4 pi epsilon naught. And then we have r cubed right here. That's what I pulled out from the brackets. And then what we're left with is z on top. And then on the bottom, z squared divided by z divided by r squared. I'll just write it that way. That's this term. Plus 1. taken to the power 3/2, okay? But here's the thing. In this problem, we're assuming that z, the distance the electron is from the center of the ring, is very, very small compared to r, which is the radius of the ring. So what is z divided by r going to be? Is it going to be a really small number or a really big number? This is going to be a very small number, right? And if I square it, that's going to even be a smaller number still, right? So the thing that you see in brackets right here is basically a tiny number plus 1, which is, to a really good approximation, just 1. Make sense? That's the approximation we're making. Go ahead.
Plus 1 on the bracket here?
It is. But I'm saying you can basically neglect this term compared to 1. So you're just left with 1. Okay? So 1 is a good approximation for what's in the parentheses. So therefore, here's what we have. Our approximation for this whole thing now, so I put the little squiggly equal sign, that means it's an approximation, just so you're clear, is q divided by 4 pi epsilon naught r cubed. Those are all constants. And the thing on the bottom is just 1, so then we just have a z overall. So to a good approximation, it's just a bunch of constants times z. This is useful. This is telling us the field is basically linear as far as z is concerned, right? It's just some constant times z. That's a much simpler thing to deal with than what we started with. I think you'd agree, right? So that's why we did this approximation. So with that in mind, let's see where we can go once we've established the approximation, okay? So any questions so far? All right, so going back, that's our approximation. We just worked it out. Ez is approximately equal to q divided by 4 pi epsilon naught r cubed times just z. So here's what's coming next. We're going to apply Newton's second law, that is F equals ma, to the electron, and we're going to focus on the z direction because we already have a sense that that's where the motion is happening, is on the z-axis. So this says that net force in the z direction is equal to the mass of the electron times the acceleration in the z direction. Okay, what can we say about the force? Remember, the electron is in an electric field, which looks like this. How do I express the force that's acting on it? QE. Yeah, I just take the charge, multiply by the electric field. That's how we get the force, remember. So I'll take the charge of my electron times the electric field, which is Ez, which we worked out. And that's what's equal to m times az. And there's no other force acting on the electron, so that's all we need to say, okay? Okay, what's the charge on an electron? We can write this, if we want, as QE equals minus the elementary charge. Remember, the elementary charge is 1.602, 10 to the minus 19 coulombs, but for the electron, it carries the negative sign. I also want you to remember what acceleration means, right? Acceleration, you can think of it in a couple different ways, but it's the rate of change of velocity. You can think of it as the first derivative of velocity or the second derivative of position. So we could write the acceleration right here as the second derivative of position. In other words, second derivative of z with respect to time. And that's what we'll do. Okay, so we're just making those substitutions in this equation. So what do we have? For the charge, we put in minus E. For the electric field, we put in the expression that we derived right here, okay? Which has a Z in it. Then on this side, we have the mass of an electron, which I'm going to write as me. And then for the acceleration, I'm substituting the second derivative of Z with respect to time, okay? Now this looks like a big mess, but actually it's not so bad because there are just a lot of constants here that we could combine them into something that's just one constant if we wanted to, and then this would look pretty simple. For example, E, Q, those are just the charge of the electron and the ring respectively. r, that's the radius of the ring, 4 pi epsilon naught, it's just one big constant. The mass of the electron is another constant. So why don't we just like put all these constants together into a single term and then not have to write a million different constants all at once, okay? So when I do that, here's what I did. I divided out the mass, so I basically collected it with this big mess. And then I added this term to the other side, so now it has a positive sign on it, okay? So what do we have? Second derivative of z with respect to time plus this giant mess of constants, which is QE divided by 4 pi epsilon naught me r cubed, and then times z. Okay, so here's what we're going to do next. I'm not going to keep writing this over and over again. I'm just going to give this a new name so we can just label it in a more simple way. And here's how I'm going to do that. I'm going to define a new constant, which is omega. Omega squared, actually, is how I'm going to say it. You'll see why in a second. But we'll say omega squared is this big constant. I'm not even going to say it again. You know what it is, okay? That's now just going to be called omega squared from here on out, okay? Which gives us a pretty simplified equation. So now we just have the second derivative of z with respect to time plus omega squared z equals 0. Does this look familiar to anybody at all? Can you tell me what it is?
It's like the general differential equation.
It's a general differential equation for simple harmonic motion. So if you see this equation, you know it's describing simple harmonic motion. If you took physics 45, this is something you'll have seen before. But if you're a little rusty on that, we'll go through why that's the case, okay? So if that's our equation, what I'm claiming is that that is an equation that describes simple harmonic motion, okay? So actually, let's just go through that on pen and paper real quick to establish that fact. Okay, so just go over to the dot cam real quick. So we have a differential equation. That just means the equation itself involves derivatives. And in solving the equation, we don't get just some number out, we get a whole function out. And that differential equation is the second derivative of z, second derivative of z with respect to time, plus omega squared times z equals 0. Okay, that's our differential equation. My claim is that the solution is z as a function of time is some kind of constant out front, which I'll call z0, times cosine of omega t. And you know the cosine function is something that oscillates, so this would be describing the electron oscillating up and down on the z-axis. So how can we check this? Well, if this works, it means we should be able to plug it right back into the differential equation and see that it actually solves the equation. So this is kind of what we call the guess and check method. And I'm not really guessing, I knew that was the answer, but I'm just trying to show you that it works, okay? So we need to take two derivatives of this thing in order to check the solution, right? So let's just go through that exercise real quick. If I take one derivative to get dz dt, what do I get? What is the derivative of this with respect to time?
Negative z.
So we have the constant out front. We pull out an omega, that's the chain rule. And then cosine gives you negative sign when you take the derivative. And we still have sine omega t, yeah? So that's the first derivative of our function. What's the second derivative? We'll just take the derivative of this guy, right? And so, yeah, what is the, let's just concentrate on this, because these are just constants in front, right? Sine goes to cosine, right? But we pull out another omega factor via the chain rule. That's how this works, right? So we have minus z naught omega squared, and then cosine omega t. So do we agree that's the second derivative? Okay, let's try it in the differential equation. The differential equation says the first term is the second derivative. So I'm plugging in minus z naught omega squared cosine omega t. That's just the second derivative we just worked out. The second term is plus omega squared times just z. So this is what we had before we took two derivatives. That's z naught cosine omega t. Well, this term is just the negative of that term. So that equals 0, and that solves the differential equation. So it works. That's a solution. Hopefully you believe me. Okay. Any questions on what we just did here? Okay. So, the solution, as we just showed, is z as a function of t is equal to z naught cosine omega t. How does the cosine function behave? It just oscillates up and down, right? So we'll start at some value of z, then we'll go to some negative value, and then back up to that same positive value, and then back down to the negative value, and that just repeats forever, basically. What does this look like? Well, I'm going to show you an animation. Okay? This is what the simple harmonic motion on the z-axis looks like. So we start at z naught, shoot down to negative z naught, back up, and then back down. That just keeps happening, right? Okay? And what is omega telling us? Like, what does this constant actually physically mean? Omega tells us how fast this is happening, basically. If omega takes on small values, this is a very slow oscillation. And if omega takes on larger values, it's a faster oscillation. Okay? So, yeah, that's basically it. What we say is the amplitude of the motion, that is just like how far do we go in each direction, is z naught. And the angular frequency is omega. And that tells you how fast we're oscillating. So those are the two numbers that really characterize this kind of motion. So we've pretty much worked out this problem symbolically. But what I'd like to do, just to wrap this up, is I'd like you to take the result we just derived, where this is our omega, and I just want to remind you there's something called period in an oscillation. So period just means how long does it take to complete one oscillation. It's just an amount of time, okay? T, the period, is equal to 2 pi divided by omega. So this is something that you might have seen in Physics 45 again. So if this is our omega and this is our T formula, I want you to plug some numbers in to actually calculate T. So the question here is, what is the period of that simple harmonic motion that we just saw, given the following values, okay? So we have the ring, let's say it has a radius 35 centimeters. Let's say its total charge, which I'm giving you as capital Q, is 67.5 microcoulombs. You also need to know the elementary charge E, which is here, the mass of the electron, which is here, and then epsilon naught, which is given here. So it's kind of a big plug and chug. Try it out, see what you get. It's going to be a very short amount of time, as you can probably guess.
is there only one solution to the differential equation? Or is there like multiple ones?
That's a good question. Sine also works, but it doesn't, there's not really a difference between sine and cosine. They're both describing an oscillation happening.
Does that electron like also do damped motion?
I'm sorry?
Does that electron also like do damped motion? This is pretty much.
Oh, damped motion?
Yeah.
Oh, yeah. There is a way the motion is damped, but it's just too much to get into right now.
Is that why we're more in phase angle as well? In the equation?
Yeah, it's not important. We just care about it, the fact that it's oscillating up and down. Yeah. Okay. Time is slipping away from us. It's almost 3 o'clock. Let's go through this. So here we have t equaling 2 pi divided by omega, correct? And omega is the square root of that big ugly set of constants. And we're dividing by omega, so what we're going to do is invert that fraction we saw earlier. So we have 2 pi times the square root of 4 pi epsilon naught, mass of the electron, radius cubed for the ring, divided by the charge of the ring, and the elementary charge multiplied together on the bottom. So let's put in what we know. That's 2 pi square root 4 pi epsilon naught is 8.85, 10 to the minus 12. Okay, I'm going to leave the units off here, but here's what I'm thinking as far as the units go. I'm going to plug in all units into this formula, and I know that I will get an SI unit out. Okay? So as long as everything I plug in is in SI units, that is meters, kilograms, seconds, and so on, I know I'll get an SI unit of time out, which is seconds. Okay? So the mass of the electron, 9.11, 10 to the minus 31 kilograms goes here. The radius of the ring, 35 centimeters, or 0.35 meters, goes here, and it's cubed. The charge on the ring, 67.5 microcoulombs, that's 10 to the minus 6 coulombs, so we have this in SI units as well. And then we have 1.602, 10 to the minus 19 for the elementary charge E. So that's kind of a big calculation to do, but who has the answer? Yeah, 3.98, 10 to the negative 9 seconds. So that is 3.98 nanoseconds. 10 to the minus 9 is nano. So in this configuration, the electron would be oscillating up and down, roughly speaking, 1 billion times every second. Okay. So do we have any questions on that? Okay. So that's just a quick calculation using the result we derived. Okay? The last topic here today, it still has to do with how charges move around inside of an electric field. But we're going to take a look at a very specific case, which is an electric dipole. And this is important. It's going to come up later, especially when we get to the lecture on capacitors. This will come up a lot. And what I want you to take away from this is just qualitatively, how does an electric dipole rotate when it's inside of an electric field? Okay, so we'll go through it, we'll work out an important result, and then after this we'll get some practice problems, okay? So here we go. Let's first define our terms. An electric dipole is basically any object that has a positive side and a negative side to it, but overall it's charge neutral, okay? So think something like this. This is the simplest way to visualize an electric dipole. You have a positive charge plus Q at one end, and you have a negative charge minus Q at the other end, and they're separated by some amount, we'll call the distance between the two charge sides L, okay? But of course, these are just equal and opposite charges, so when we add them together, we get zero net charge, but there is a separation of positive and negatives overall happening. We've seen this kind of thing before, right? So this could be potentially a molecule, right? So let me give you some examples of molecules that behave in this sort of way, like electric dipoles. And basically, whenever you have a molecule where the electrons are not evenly shared, in other words, the electrons tend to hang out next to one atom more than others, you have an electric dipole. Even if the molecule is overall neutral, because the electrons tend to favor one side, that side becomes slightly negatively charged, and the other side picks up a slight positive charge. So like CO, carbon monoxide is an example of this. The carbon atom tends to hang on to the electrons in the covalent bond a little bit more than the oxygen, so that becomes a negatively charged side, and this becomes a positively charged side. Same with water, H2O. That's a molecule which we can model as an electric dipole because the oxygen atom tends to hang on to electrons more than the hydrogens. So this picks up a negative charge and this picks up a slight positive charge. But not every molecule is like this. Okay? Let's think about something that's like more symmetric, like O2. This is the oxygen you breathe in. So since we have two oxygen atoms, they have the exact same tendency to hang on to electrons. So it's not like electrons will favor one side or the other, right? So this is not a dipole because we don't have this separation of charge happening in this type of molecule. So does that make sense, what a dipole is and what these examples are telling us about dipoles? Okay, so we're not going to look at any like specific example for what comes next. We're just going to use this sort of simple model that you see up here, okay? Okay, so I'm going to ask you a question, or actually a series of questions. We have three different diagrams. In each one of these diagrams, you have an electric dipole inside of an electric field, okay? So my question for you is, for each one of these examples, what kind of torque is the dipole experiencing? And remember, a torque is something that's going to induce the dipole to rotate, right? So here's how I would suggest thinking about this one. Let's actually work out the first example together, and then I'll send you off to work on the last two. So it should be pretty clear how this goes once you see the first example, okay? So for the first example, let me ask you a question. The E field that we see is pointing to the right, isn't it? So what kind of force, what direction is the force that's acting on this negative charge here? It's because it's negative, it opposes the electric field, so the force is going to the left. What about for this positive charge? What direction is the force? Going to the right. So can you see how if I took some object and I like took the top of it and pulled it to the right, took the bottom of it, pulled it to the left, it would rotate? Yeah. Which way would it rotate? Yeah, so this would rotate counterclockwise like this. That makes sense? All right, so try out the second one for yourself. So this one rotates counterclockwise. Which way does this one rotate? Well, take a minute. I'll give you like 30 seconds just to think on it, and then we'll vote, okay?
So the first example, it's like straight up. Would it like
Yeah, that is.
So
There's still one there.
Stable
I forgot which one was which, but
All right. So what do we say about number two? What's the answer? I heard both clockwise and counterclockwise. So let's go through it. It should be in this case clockwise, right? So here, this is example 2. And I'm just going to draw a picture. The picture will answer the question for us. So in this picture, we have the negative charge kind of down here and the positive charge up here in the electric field, which is pointing to the right. So I'm going to label the force on the positive charge F positive. We know that one goes exactly with the electric field. I'll label this one F negative. We know it goes exactly against the electric field. Okay, so here, just take, like literally take your pencil, put it in front of you, right? Push this end to the right, push this end to the left. Which way does it rotate? Rotates clockwise, right? So clockwise rotation. Feels a clockwise torque, okay? What about the last example?
Zero.
Yeah, so this one is not feeling any torque at all, is it? Because if we consider the forces acting on it, so this one, again, it's negative. It feels a force going against the field like this. This one feels a force going with the field like that. So in this orientation of the dipole, it's kind of just being pulled apart, but it's not induced to rotate. Yeah.
So are they all gonna end up in that state, or are they just gonna fix themselves?
Okay, so you see where this is going, right? My point is, right, if we start off with our dipole like this, it feels a counterclockwise torque, right? And that makes the positive Q go with the field, the negative Q against the field, right? If we have it like this, okay, it feels another torque, but that still brings it to that same orientation where the positive Q is going this way, negative Q is going this way. So the whole point of this, which we'll get to over time, is that dipoles in an electric field, they tend to align in a certain way. They're all kind of induced to align in the same direction, okay, because of this torque. But we'll go through the details of that. Okay, so now we're going to work this out in a more kind of mathematically precise way. So we have generally this picture. We have an electric field. Let's just say it's going to the right, and we have our electric dipole. Okay. What we're going to do to keep track of how the dipole is oriented is label an angle theta on the diagram. So let's just be really clear about what this angle theta is. It's the angle between this line, which goes to our positive charge, and the direction the E field is pointing in like this. You see that? So that's what theta means. Now, L, that's going to be the length from one charge to the other. But D, that's going to be the distance to the center of the dipole from the end. So this point at the very center will be our center of mass. We're going to assume there's just an equal amount of mass on either side, so the center of mass is right there in the middle. Okay? Now, let's label the forces that are acting on each charge. So we have F positive going with the field, like we just said. I'm going to write this in the following way. Since this force is going in the positive x direction, according to our picture, this would just be positive Q times E, because that's how we get the force given a charge and an electric field. And it's going in the positive x direction, so there's an I hat unit vector on top of that, right? For F minus, the force on the negative end of the dipole, that's going to be minus Q times E, and that's also picking up an I hat unit vector because it's going in the negative Z direction. Okay? Good, are we good so far on this? Okay. So if you think about just how these forces add together, clearly if I add this force to this force, they cancel out to give me 0. So it's important to note that there's no net force acting on the dipole, which means the dipole is not going to be moving a large distance one way or another. More precisely, the center of mass of the dipole is not going to be what's moving, okay, because there's no overall net force on it, so the center of mass doesn't move. The only thing that happens is it might rotate around its own center of mass, but the center of mass is not going to be experiencing any kind of force that moves it one way or another. Okay, you guys remember how torque works? We're going to be dealing with torque from time to time in this class, and this is our first kind of time seeing it. But there is a formula that you should know from Physics 45 for torque, which is torque given by this letter. What's this Greek letter right here? Tau. Tau is equal to r times f times sine of theta. So just for what we're doing here, we have to keep track of the direction of a torque. So we'll take any kind of clockwise torque to be positive and any counterclockwise torque to be negative, just so we can keep track of directions, okay? Okay, what does R represent, by the way? That would be the distance from the center of mass out to where the force is being applied. So like that would be the distance here, and for the other one, this would be the R distance. And then if F, then of course F is your force, and theta is this angle here. Okay, so let's write down a formula for the net torque on the dipole about its own center of mass. So we're basically adding up two torques, right? We have a torque due to this force up here, which we can use this formula to give us, and then we have another torque due to this force right here. We'll use the same formula. Now both of these are actually in the same direction. They're both like clockwise torques. So we'll give them both a positive sign. So for the first one, this is the torque due to the force on the positive charge up here. R, that's just the distance d between the center of mass and the charge. So that's what I'm plugging in for R. For the force, I'm plugging in Q times E. That's just the magnitude of the force. And then we have sine of the angle theta, right? For the next one, my distance R between the center of mass and the negative charge, if the whole distance here is L, then this distance is L minus D. You see that? So I'll have L minus D times QE times sine theta. And we can clean this up just a little bit, right? Like for example, I have D, Q, E sine theta here, positive. But over here, if you distribute this minus D along with these other terms, you have minus D, Q, E sine theta. So basically, this term here cancels with this term here. And the only thing you're left with is L times Q times E times sine of theta.
What happens to the negative that was on the force on top?
So in this formula, because we're talking about a torque now, right? The direction of both of these torques is actually the same. Let me just go over this real quick. Do you guys remember the right-hand rule for torque? You start at the axis of rotation, which is right here. Then you take your fingers and then you point out to where the charge is, and then you curl in the direction of the force. So that would be like a clockwise torque, right? And then for the other one, you do the same thing. Start here, point your fingers out to where the charge is, then curl in the direction of the force, and it's still in the same direction, right? So that these two torques are in the same direction. Yeah.
Yes, can you express D in terms of L?
Yeah, so just in terms of L. Yeah, the D just cancels out. So when we cancel this term with this term, is this what you're asking? We express this just in terms of L?
No. Can we say the D equal X divided by 2?
You could do that, but actually it works even if you don't assume that. It just drops out regardless. Okay? So we have QEL sine theta. That's the torque exerted on a dipole, which is inside of an electric field. Okay? And that torque, remember, is going to induce the dipole to rotate. That's what it does. Okay. So with that said, let's take a look at this result and see what it's telling us. Okay. So there's something special that happens in this formula when theta is equal to 0 and when theta is equal to 180. Because here, what is sine of 0? It's just 0, right? So if the angle is 0 degrees between our positive charge and the E field lines, then there's no torque. We'd agree? Because plug that into this formula, you get 0 torque. So in other words, it's just happy to sit there in this orientation. There's no torque on it if you put it in this orientation. Also, same goes for 180, right? Sine of 180 is equal to 0. So if you plug in 180 to this formula, you also get 0 torque out of that. Okay, so this is what it looks like. Let me just show you when theta is equal to 0. It means we have a positive charge going towards the direction of the electric field and the negative charge facing away. This is what it looks like when theta is equal to 180. It's just that flipped, right? So the negative charge is now going in the direction of the E field, and the positive charge is going against it. So these are both what we call equilibrium positions because the torque is 0 when the dipole is in that position. Okay, so it's in equilibrium with no torque acting on it. But I'm claiming here that one of these equilibriums is stable and the other one is unstable. What do I mean by stable? If it's stable, that means if I knock it away from this position just slightly, it's going to go right back to that position. Unstable means if I knock it away from this position, it's going to go very far away from that position. Okay, and let me just sketch out a picture which will hopefully convince you why one of these is stable and the other one is unstable. Okay? So, let's draw some pictures here. Okay, so I'm claiming that theta equals 0 is stable. That means, as we said, if I get slightly away from theta equals 0, that it's going to go right back towards theta equals 0. So here's what that looks like. Here's our positive Q. Here is our negative Q. Our E field is going to the right, just that's how we're drawing it in this picture. And remember, the angle theta is this one right here, between the direction of our E field and where the positive charge is lining up. So what I'm showing you here is we're pretty close to theta equals 0, but we're knocking it slightly away from theta equals 0, right? So in this orientation, remember, the positive charge feels a force going with the field. The negative charge feels a force going against the field. So what kind of torque is happening?
Clockwise.
Yeah, and that torque is bringing it right back towards theta equals 0. So if you're at theta equals 0 and you get knocked slightly away from theta equals 0, you're going to feel a torque that brings you right back. That's why we say it's stable, okay? In other words, it really wants to be at theta equals 0, right? Because any slight motion away from that brings it back. Okay, theta equals 180, I'm claiming is unstable. Meaning it's not going to stay there for very long if you knock it away from theta equals 180. Okay, so what does that look like? Let's imagine, so theta equals 180 would mean my positive Q is like over here. But we're going to not be exactly at that angle, something just slightly away from it. So remember, the E field in this picture is going to the right. And this is theta being kind of close to 180, but not quite, right? Does that make sense? So the force on our positive Q is going with the E field. The force on our negative Q is going against the E field. That actually induces this type of rotation, which brings it back to this orientation where theta equals 0. You see what I'm saying? So pretty much no matter what you do, the dipole is feeling a torque that wants to bring it towards this orientation. Okay, it's really important to see. This orientation where the positive charge is going with the E field lines and the negative charge is going against it. That's really what the dipole wants to do, in a sense. Okay? So, that's what it looks like from one dipole. What if we have a whole bunch of dipoles? Okay? This is what we call a dielectric material. And this is something that's found inside of a lot of electronic equipment, specifically capacitors. They're all filled with dielectric materials. The dielectric material is just anything that consists of a huge number of dipoles. You can call these polar molecules. same thing. So again, what is a dipole? It's just something that has a positive end and a negative end. And we have a whole bunch of them. So what does that look like when there's no electric field present? Well, basically, all of these molecules are just randomly oriented. There's no preference for them to align one way or another. So this is what you want to think about when there's no electric field. Just randomly oriented dipoles, no particular orientation, okay? But when you do turn on an electric field, as we've seen, the dipoles tend to favor a certain orientation, right? That is with the positive end of the dipole going along the electric field line. So if we take this material and then we turn on an electric field, we place it in the presence of some electric field, the dipoles line up with that electric field in this way. Okay? So this is something that we're going to see a lot in like 3 chapters from now when we get to capacitors, as I mentioned. But I hope you just see why this is the case, why the dipoles are aligning in this way. So do we have any questions on that? Okay, so go ahead.
One question with regards to the torque. Will the angle change depending on the direction of the electric field?
Yeah. So we defined the angle in terms of which way the E field was pointing. But the point is, what that equation tells us is the dipoles want to align with the E field, regardless. So if the E field's pointing this way, they'll align this way. If it's pointing this way, they'll align that way, and so on. Okay. Anything else? Okay. So go ahead, Brian.
Would it still happen if the E field was like not like completely straight?
What's up?
Would that still happen if the E field was like not completely straight?
Yeah. So right. If the E field were not just kind of uniformly pointing in one direction, the dipoles would sort of track whatever the E field's doing. Yeah. So like I said at the outset, we have some practice problems we can get through today. I think we have about 25 minutes. So you should know, if you don't know already, all of the lectures that I give to you have these end of lecture practice problems, okay? And we usually go through a few of these if there's time, but we're pretty much never going to get through all of them, okay? So you can think of these end of lecture questions as there for your own benefit to study at home, just some extra problems to practice with. Especially when tests are coming up, you want to go through these just for extra help. Does everyone know that the answers to these questions are posted on Canvas? If you go into the lectures folder, there's a document that just has the answers to all these problems. So if you are using them to study, you can try working them out and then see if you get the right answer, okay? So with that said, let's try to get through a few of these. This one involves point charges. I think we've seen some of that today. Let's pass on that. Okay, this was the quiz problem. Okay, sometimes I repeat problems, something no. So we don't have to go through that again, do we? Okay, maybe how about this one? This one is kind of similar to something you saw in the homework, so I think it's worth going through because I graded the first homework and some people missed a question that was pretty similar to this. So we have a ball, mass M is 95 grams, and the charge is 45 microcoulombs. And it hangs from a string like this. So this is the charged ball. This ball is inside of a uniform electric field, pointing to the right, as you see here. And the magnitude of this field is 3.75 times 10 to the 4 newtons per coulomb. So 2 questions about this. What is the angle that the string makes with the vertical? And then what is the tension in the string? So for this problem, we are not going to neglect the force of gravity. We're going to actually account for it, okay? So because time is limited, I'm going to start the problem with you, then send you off to finish it, and then we'll reconvene, okay? So the first thing we should do in a situation like this is, of course, draw a force diagram. So can everyone tell me, if we think about the charged ball right here, what forces are acting on it? Tension. Tension? In what direction does tension act?
Towards the string.
Yeah, tension always acts along the length of the string. So it's going to be pointing up and to the left like this. What else?
Gravity.
There's gravity pulling it straight down. And then
Electric field.
the electric force, this is a positive charge, so it's going to be feeling a force going with the field. That's what's responsible for pushing it out this way in the first place, right? Otherwise, it would just hang like this. Okay, so let's take those forces, put them on a diagram, and then see how we can solve from there. Okay, so here is the charged ball. Like we said, the force of tension is going along the string. I'll call that Ft. Force of gravity is going straight down, Fg. And then the electric force, which I'll call Fe, is going to the right. We agree? Okay, let's draw the x and y axes just for reference, like this. All right. So the electric force only points in the x direction, the gravitational force only in the y direction. Tension kind of has both components, so let's break this into those two components. Now this angle up here, remember that's the angle theta which our string makes with the vertical, okay? So this would be Ftx going along the x-axis, and this would be Fty going along the y-axis. That's how we would break that force into components. Okay, let me ask you a question about this charged ball. What's the acceleration of it?
0.
It has 0 acceleration because it's stationary. It's not moving, just hanging there stationary. So what we can then do is F equals ma. We can do it in the x direction and we can do it in the y direction. But when it comes time to plug in an acceleration, we know it's just 0, correct? So let's take one more step here. How about I take my y equation first? Doesn't matter which one you do, but let's start with y. What are the sum of the forces in the y direction?
Tx.
So the y direction.
Or Ty and Fg.
So you have Fty, which is the positive y direction, minus Fg, and then that should equal 0 because we're stationary. Okay, can someone tell me, how could I express Fty in terms of this angle theta? Because we don't want Fty, we want the angle theta to appear in our equations.
C cosine theta.
Yeah, so check it out. Fty, if we think about this right triangle we've constructed, it's the adjacent side, right? It's adjacent to our angle. That means it goes with cosine, correct? So I'll write this as Ft cosine theta. And then how do I express the force of gravity, generally speaking? This is just m, the mass of the ball, times g, acceleration due to gravity, equals 0. So that's going to be our y equation. We'll do something with it later, but just keep it like this for now. What about our x equation? So what is the sum of my forces in the x direction?
This is sine theta
Force tension in the x direction.
Yeah, so let's take it in small steps. So in the positive direction, I have Fe. And then going along the negative x-axis, I have Ftx. So I'll write this as Fe minus Ftx. And then again, set that equal to 0 because we have no acceleration in the x direction. Okay, Fe, how can I express that? It's the charge Q on this ball times E, the strength of the electric field that this is inside of. Okay, electric force is just Q times E. Okay, what do I do with Ftx? So Ftx is the opposite side, so it goes with the sine of theta, doesn't it? So it's Ft sine of theta, and that all equals 0. Okay? We're good on this so far? All right. Let's take another step. How could I go about solving for theta here? So the thing about theta that makes this difficult is it's inside of a sine function, and then it's also inside of a cosine function. And I'm trying to just isolate theta somehow.
You could set the two equations equal to each other since they're both equal to 0. So
Yeah. Yeah, so I could combine the two equations essentially.
Yeah, like say FT cos theta minus mg is equal to QE minus.
But then that would be a good start. But I would still be faced with this problem of having a sine theta and a cosine theta when I just want to sort of combine those into one thing. How can I combine sine and cosine? Tangent might be a good idea, right? So if I write, and that would just be the next logical step in what you're saying. I'm going to write it this way. I'm going to write it as tangent theta is equal to what?
Sine over cosine.
It's sine theta over cosine of theta. So here, I can take this equation right here and solve for sine of theta, can't I? What would that give me if I took this equation and I solved for sine of theta? Yeah, so take the x equation, just rearrange it to solve for sine of theta, and you'll find it's QE divided by FT, right? And then take this equation, solve for cosine theta, and what will you find that that's equal to?
Mg over ft.
Yeah, that would equal mg over ft. We agree? So then what do we have? We have tangent theta equals QE divided by mg, correct? Okay, so calculate that answer. Get theta and get ft. Tell me what you get, okay? And I'll take it back to the slide so you can refer to the numbers, okay? So take a minute or two to work this out. That works too. Yeah. Just slightly different source for the big same answer. Does anyone have the angle?
61 degrees.
Yeah, so you should find that angle comes out to 61.1 degrees. Okay, that's just kind of plug and chug with the equation we have. Now try to find the tension force. The same set of equations we came up with can be used to find the tension force. So here, let me just put that on the page for completeness. We have, not going to show the whole calculation. If you plug in the numbers, solve for theta, you'll get 61.1 degrees, okay? Now that we know this, or I said 61.1, that's not what I wrote down, 61.1. Okay, 61.1 degrees. Now, I could really take any one of these equations, the x equation or the y equation, and just, oh, can't see that, x equation or the y equation, and then just solve for ft. How about we do the y equation right here? So if I take this and I solve for ft, what do I get? Or just symbolically, if I solve for ft, mg over cosine theta. And now that you know what theta is, you can plug the numbers into this formula and you'll get out ft. Does anyone have that number yet?
1.93.
That gives you 1.93 newtons. Okay, so I skipped over some of the plug and chug steps, but I'm sure you can figure that out. Make sense? All right. We have a little bit of time left, and I hope we can get through maybe one of these integral type problems, because those are tough. How about this one, okay? This is similar to a recent homework problem, and I think it'll be beneficial to see it. So we'll see how far we can get with this. Here's what we have. We have a total charge Q, which is uniformly distributed on 3/4 of a ring, which has radius r. That ring lies in the xy plane. The question is, calculate the electric field right here at the origin. Okay? So, you know how we usually start with problems like this. We try to determine if we can just make an argument from symmetry that one or multiple components of the E field will be zero. Can we argue that the x component will be zero in this case? We can't, actually. What about the y component? We can't do that either in this case. I'll show you in a second how to set this up, but the overall E field is going to be kind of pointing off this way. And so we don't have this sort of symmetry where we can cancel either the x or the y component in this case. So what we're going to do is just calculate both of them without assuming either one is zero. Okay? So let's go to the dot cam for that. So let's copy down the picture. We have 3/4 of a ring lying in the xy plane. And the ring starts up here, and then it ends down there. Okay, that's what we have. First thing to do is locate a charged element on this ring. Doesn't really matter where I draw it. I'm just going to draw it down here for this solution. But it doesn't matter where I draw it because eventually we'll integrate over all of them. Okay? Now we're going to draw a line extending from that charge element to the field point, which is right here. And then what we're going to do is show that this dq is creating a small infinitesimal electric field, which we call dE. And the way this works is it points directly away from the charge, because we're assuming this charge is positive for this problem. Okay? So there's dE. The next thing I need to do is take this dE vector and break it down by component. So in other words, this will have some kind of x component to it, and it will also have some sort of y component. Okay? So this would be dEx, and this would be dEy. So we can label an angle right here, which I'll call phi, which basically also appears here, by the way. We can think of phi as just taking us to the charge element. So for example, if phi were 0, the charge element would be right here. If phi were pi over 2, it would be over here, and so on. It just tells us what angle to go to get to the charge element. But let's also note that this dq here, it spans a certain angle, okay? So we can call that angle d phi. That's what we typically do, because it's an infinitesimal angle that it takes up along the ring. All right? So last thing to note is this is the radius of the ring. Okay? So I think we've labeled everything we need to label. Now let's start writing down some equations. If I were to pick out the component dEx, how would I do that given this right triangle here? Yeah, so dEx is the adjacent side right here. So the adjacent side goes with cosine. It's the magnitude dE times cosine of the angle theta. And by the same token, dEy is equal to what?
DE sine.
Would be the magnitude dE times sine of the angle phi, like this. And what do I do with the magnitude of dE? This is always the same in Coulomb's law.
KdQ over R squared.
Yeah, this is K times dQ divided by R squared, because this infinitesimal element of charge is basically a point charge, and this is the formula for the electric field due to a point charge. The only difference is we're writing it as dQ as opposed to Q, okay? So let's figure out what comes next. Okay, small r, remember that represents the distance between your charge element and the field point P. So what is that distance? It's just the radius of the ring, right? So when I say small r is equal to big R, I'm just saying every single charge element, regardless of which one we pick out, is this same fixed distance away from the point. So in other words, constant distance away from all these charge elements, okay? The other thing we need to worry about is dQ, okay? So this can be tricky sometimes, but here's how we're going to think about dQ. The total charge on this ring is uniformly spread out, okay? So that means there's no part of the ring which is more dense in terms of how packed the charge is compared to any other. It's uniformly spread out. So because of that, I should be able to write down this relationship, okay? And I'll write down the equation, then I'll explain what it means in words. dQ, which is this tiny element of charge, divided by Q, which is the total charge on the entire section of the ring, that should be equal to d phi, this tiny angle spanned by the charge element, divided by the total angle that this takes up. Now, what can I say about that total angle?
3 pi over 2.
Yeah, so here, let's work it out. Total angle, right? Well, we have 3/4 of a ring, and a total ring would be 2 pi, right? So yeah, we have 3 pi over 2. That's where that comes from. So you're correct, I'm just showing where that comes from, okay? Okay, so on the bottom of this, our total angle is 3 pi over 2. Does this make sense? This is saying whatever fraction of the total charge we're taking up with this little element, we're taking up the same fraction of the total angle. That's just what it means to be evenly spread out. So in other words, if this takes up 1% of the entire charge, it's also spanning 1% of the entire angle, okay? So if we solve for dq, given that formula we just wrote down, here's what we get. So dq is equal to 2q divided by 3 pi times d phi. We agree? So a simple rearrangement of this equation to solve for dq. And let me just write, this equation comes from the fact that we have evenly distributed charge. That's where it came from. Okay, so now let's write our formula for dex with all the substitutions. Dex is magnitude de, which is k times dq, which is this thing. So I'll plug in this for dq. That's 2q over 3 pi times d phi, divided by little r squared, but in this problem, that's the same as big R, the radius of the ring, so I'm going to put that in on the bottom, okay? And then for the x component, we had cosine, right? So let's just separate out what's constant here and what is not constant. What's constant is all of this stuff, which is 2k times q divided by 3 pi r squared. That whole thing is just a bunch of constants, right? And then we have cosine phi d phi. Do you agree? Okay. For DEY, I'm going to say dot, 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 because it's the same exact thing, except what's the one difference? Except this cosine is a sine, okay? So same exact formula you'll end up with, which is 2kq divided by 3 pi r squared, except now we have sine phi d phi. So to recap, these are the x and y components of this infinitesimal bit of electric field contributed by this charge element dq. So we're not done yet. We have to now integrate, right? Because we've only accounted for just one little infinitesimal element of charge. If we integrate over the entire ring, then we'll get the overall effect of all of those charges on the ring. So Ex is nothing more than the integral over dEx, which is this guy, right? So we already separated out what's constant, so I'm going to just pull that out to the front. We have 2kq divided by 3 pi r squared. Then we have integral cosine theta d theta. If we can just evaluate this integral, we'll have our answer, but we need to put limits on it, right? What can I say for the limits of integration for this guy?
Pi half to 2 pi.
Okay, so let's just be clear about the way I set this up. This is important. Phi equals 0 is us being right here. And then phi increasing means we're going this way, right? So we actually have to go backwards to get to the start of the ring. We have to go backwards by pi over 2. So that would be like minus pi over 2, where the ring starts. And then we'd have to go half a circle around, which is pi, to get to where we end up. Okay, so that's what we set as the limits. Does that make sense? Yeah.
Would it make any difference if you just put it like 0 to 3 pi over 2?
Yeah, it would, because it matters which line we're measuring phi off of. Yeah, it does make a difference. So since we're measuring it off this line, we start at minus pi over 2 and end up at pi. Okay? So,
Can you repeat that how we get the pi over 2?
okay, so see how we are measuring the angle phi?
Yeah.
If we go forward this way, that's considered a positive angle. If we go back this way, that's considered a negative angle, because we're going in the opposite direction. And how far do we have to go from this line? Pi over 2, right? So that's where the minus pi over 2 comes from. Starting at this line, how far do we have to go to get to here? Pi. That's where that comes from. Okay? Okay. So EY, remember it's the same exact thing, except the integral has a sine of phi inside of it. So we have 2kq divided by 3 pi r squared. Same limits because we're integrating over the same ring. And then we have sine of phi d phi. So we're out of time. We don't have time to actually crunch the integrals here, but that's kind of the easy part compared to setting it up, okay? So I'll tell you what the answers are for both. If you compute the integral, here's what you'll get. 2kq divided by 3 pi r squared. Okay, that's it for today. Next week we'll start Gauss's law.